Introduction to vectors. Vectors are, it's like numbers with a direction. It started when Newton realized that if you have a single object and two people are pulling with different strengths, let's say one person is pulling this with 3 newtons and the other person is pulling with 2 newtons. If they're pulling in the same direction, then the strengths just add up 3 plus 2, so this object will be pulled by 5 newtons. However, he realized that if they are being pulled in different directions, then the sum of these two forces have to be calculated using what's known as the parallelogram law. So 3 Newton, 2 Newton, put them like this so that their initial points match, and you draw a parallelogram, and the result is this. This is what we call the resultant vector. And therefore, he realized that forces not only have numbers, but it also has direction. So he named these vectors. Now, you might notice that these are kind of acting in a different point of the item, and I just put it like that. And that's another consideration of Newton. He realized that when you try to describe the motion of a particle, they can just basically think of this particle as a point particle at the center of mass. So let's say this is the center of the mass. You can move this over here, move that over here, and make this picture and add them up. So another thing that he realized is that these vectors needs to be able to be moved around. So when you have this vector, you have to bring it over here, bring it here, so that if you want to add them, you can draw a parallelogram. So you can add, okay? Okay, there's another way to add two vectors, which is to add as a triangle. And the way you do that is instead of bringing this to the same initial point, you can bring this so that the second vector has the initial point at the terminal point of the first vector. And if you do that and connect the very first and the last, this is the same resultant vector you get from here. And you might think there's no need for such two different ways to get the same resultant vector, because after all you get the same answer. However, there are indeed cases where triangular law of addition is easier. Okay, that's the physics description, but often in Calculus 3 we are going to use coordinate system of vectors more. So let's say you have a vector that's given by the initial point at 0, 0, and say 2, let's say 3, 2. So here's the point 3, 2, and here's 0, 0, and let's say you connect these 2 points to get a vector. This quantity definitely has the magnitude and also the direction, right? Let's just name this as V, and I usually put an arrow on top for vectors. So this vector has the magnitude, and that's given by the magnitude is given by the square root of each of the components. Oh, I should really just say Vx. Yeah. So I shouldn't put an arrow because I want Vx, which means it's a scalar. It's just a regular number. In that case, you shouldn't put any arrow there. Vx is 3 and Vy is 2. These are the components, x and y components of this single vector. And when you have these components, you simply add their squares and take the square root, and that gives you the 9 plus 4, so that gives you square root of 13 as its magnitude. And this symbol, double bars before and after, that's this operation is called the norm. Now I'm going to be using norm, magnitude, and size interchangeably. They should mean the same thing. It's just the length of a vector. And then it also has a direction. So this is a vector whose magnitude is square root of 13, and it has this direction, right? Often you would try to represent the direction with respect to the positive x-axis by thinking of this angle theta, right? That angle theta is given by the arctangent. Just using SOHCAHTOA on this right triangle will reveal that since tangent is opposite over adjacent, tangent of theta is 2 over 3, and therefore theta would be tangent inverse of 2 over 3. Okay, so you can say that this gives you the direction, and this gives you the size, and therefore this is indeed a quantity that has a direction and size, so it's a vector. Okay. Now, when it's a vector, you want to write using this angled brackets. So write it like 3, 2 with angled brackets. Now this is not always the standards. Some books would just put 3, 2 with parentheses and use the word points and vectors interchangeably, because after all, in a purely math perspective, a two-dimensional vector is just two numbers where you have this additional property that you can add things or subtract things or multiply by a single number. Those are called vector operations. I'll explain a little later. Okay, now for three-dimensional vectors, you would need x, y, and z. So let's say this is x, that's y, and that's z. And you could have a point in space like 1, 3, and 2, and you can connect them. That will be a vector. So you might have a vector that's like 1, 3, 2. And to talk about the direction is a little more tricky. They use the direction cosines. If you have this angle, and this angle from each axis, you can talk about cosines of that angle. That's not too important. Let's just learn how to get the magnitude. In this case, you have 3 components, so you take 3 components, squares, and add them. Both of these formulas just come from the Pythagorean theorem. You can check. It's very easy. All right. Now, what's important is how do you get a vector if you're given an endpoint? So here's an example. Let's say you have a cube of size 3. Okay, so this is 3, that's 3, that's 3. Which means this point will be, let's say this is x, y, z. This point is on the YZ axis, so that means its x coordinate is 0. So this point here will be 0, 3, 3. And this point I said 3, but really if you roll it down in full coordinates, it's on the x-axis, so the value of z and y are 0. Z coordinate and y coordinate will be 0, so you get 3, 0, 0. Now think about a vector that's obtained by connecting these 2 points. Okay, let's call this as v. Now that certainly has a direction and magnitude, that's a vector, but it's a little different than what we were doing in the previous page because it doesn't start at the origin. Okay? In that case, is there a way to write down the components of this vector? Oh, there is. The way you get any kind of vector, if you know the two endpoints, is by doing this formula: terminal minus initial. And because the terminal point is 3, 0, 0, and the initial point is 0, 3, 3, if you subtract, and by subtracting I mean component-wise subtraction, so 3 minus 0 is 3, 0 minus 3 is negative 3, 0 minus 3 is negative 3, and that is this will be the vector. Okay, and indeed, if you took another picture where you had the x, y, z axis, and you went 3 steps in the x direction, but then negative 3 direction this other way, 1, 2, 3 that way, and then negative 3 in the z direction, also minus 3, 1, 2, 3. So this is the point 3, 3, negative 3. And if you connected the origin with this point 3, 3, negative 3, then you'll see that this vector is exactly the same as that vector. All you have to do is just move this around so that the initial point is no longer 0, 3, 3, but now it's at the origin. Okay, so that's how you get a vector when you're given the endpoints. Okay, sometimes you're given a vector and you're given a magnitude, and you might be given like the direction of v is 30 degrees from x-axis, positive x-axis. What is this vector? And the solution would be just simply use the fact that if you have 30 degrees, you can think of this unit circle, and think about the unit circle. And the unit circle, when you have 30 degrees, it has cosine 30 degrees, comma sine 30 degrees as the point on the unit circle, right? So in that case, that's same thing as radical 3 over 2, comma 1 over 2. Those are the cosine 30 and sine 30 values. And since this has length 1, you can multiply by 7 in order to get a length 7 vector that's in the same direction. So this vector will be like 7 times. So instead of being 1, now this vector v will be 7 times this vector. Okay, so that will be 7 times radical 3 over 2, 7 over 2. Okay. Alright, so now let's talk about some properties of, the basic operations, vector operations. If you have vectors written as components, you can add two vectors. So let's say 3, 4. You can add to this 2, -1. Then that's this component-wise addition. 3 plus 2 is 5. 4 plus -1 is 3. Okay, number 2. You can also multiply. I just showed you something we call the scalar multiplication. You can multiply by a regular number. Regular numbers, usual numbers that we know of, are called scalars. So if you have 2, -1, you can multiply by 3, and that gives you 3 times 2 is 6, 3 times -1 is -3. So this one is called vector addition, and this is called scalar multiplication. In fact, any object that has this property of being able to add them, and you have some way of multiplying a number to it, scalar multiplication. Well, there are some other basic axioms that come with it. So if you write down all the properties that addition should have, one of them being like you can commute them, like a plus, if you have vector u plus vector v, that's the same thing as switching them around and say v plus u. There's a associativity, meaning that if you have 3 things added, you can put parentheses around. You also have things like scalar multiplication by 1 doesn't do anything. So there are like something like list of 10 properties for both vector addition and scalar multiplication, and anything that satisfies them is a vector. And a vector could be 2-dimensional, just like what I showed you. It could be 3-dimensional. Sometimes people use 4-dimensional if you're doing Einstein general relativity, and it can go even more, like 5, 6, 7. It's very amazing, but people realize that they can actually talk about vectors that are infinite dimensional. The idea of infinite dimensional vectors became very fruitful when people started thinking about the Fourier series that you're going to learn later. And it's a very, very long story, but these vectors are actually used to compress images and sounds and all that. So actually you're able to watch this video because all the recordings are compressed so that it can efficiently be transferred to your computer or a cell phone by compressing the data to a small size. And the idea there is Fourier transform, which is like thinking of data as vectors. Okay, well, that's a long story, but all I want to say was that vectors are very powerful.